In this video, I'll be doing LeetCode Biweekly Contest 28 and explaining my solutions. Alright, let's go over the problems from Biweekly Contest 28. I did pretty well in this contest. I got rank 188, but there were only about 6,000 people competing, so maybe it means a bit less. But it's still good. Problem 1. Final prices with a special discount in a shop. You're given the array prices, where prices I is the price of the ith item in a shop. There is a special discount for items in the shop. If you buy the ith item, then you will receive a discount equivalent to prices j, where j is the minimum index such that j is greater than I, and prices j is less than or equal to prices I. Otherwise, you will not receive a discount if j does not exist. Return the array where the ith element is the final price where you will pay for the ith item in the shop. Okay, so yeah, for each element, we find the next element which has a price lower than it, and then we subtract that off from the original price to get the discounted price. And if it doesn't exist, then we don't subtract anything. This is pretty simple. We do an n-squared algorithm, and we just brute force it. So yeah. Problem 2, subrectangle queries. Implement the class subrectangle queries, which receives a rows times columns rectangle as a matrix of integers in the constructor and supports two methods: update rectangle, which updates all values in a subrectangle with a new value, and get value, which returns the current value of the coordinate row call from the rectangle. We could just do an n-cubed algorithm here and brute force actually implement the rectangle, but what I do here is we store the original rectangle so that we know what happens if there's no queries to update. Otherwise, we maintain a history of all the update queries we've received so far. That means storing the top left and bottom right coordinates and the value itself. So then when we are prompted to get a value, we look for the most recent update in the history that involves the square that we want to find the value of. And once we find that most recent item in history, we can look at the value of the update, and that means this square has been updated to that value. If we can't find any items in history that have modified this square, then we just return the original value, and that's it. So I think this is a bit faster than an n-cubed algorithm, although it involves storing all the previous queries, which, it's not a lot because there's only 500 operations. Problem 3. Find two non-overlapping subarrays, each with target sum. You're given an array of integers r and an integer target. You have to find two non-overlapping subarrays of r, each with sum equal to target. There can be multiple answers, so you have to find an answer where the sum of the lengths is minimum. If you can't find any, then return -1. So we split this problem into two parts. The first part is creating a function that finds the subarray which has minimum length but is equal to target, and the second part is dealing with the actual array itself. So first, let's talk about the function. The function is basically like the classic two-sum problem, except this time we're doing it with any number of numbers, but they have to be in a consecutive subarray. So basically, we have a prefix sum array, and then we have a set of prefix sums. Prefix sums are basically you sum up the first n elements, and that's the nth element in the array. And that can be useful for determining range sum queries where you have to find the sum of a range in an array. So this means that if we know the end index and the start index, we can take prefix end minus prefix start to get the sum of the range between start and end. This means that we can loop through the entire prefix array, and this index that we're keeping track of is the end. We want to find a value of start such that prefix end minus prefix start is equal to target. And we can manipulate this equation, which is pretty simple, so that it says prefix end minus target equals prefix start. So we're looking for prefix end minus target, and that's this line over here. If prefix end minus target will actually be in the prefix sum array, then we can actually find a start value. And this means we're going to use a set to have more efficient operations. So what this means is if we have an end array that has a valid start array such that the sum is going to be equal to target, we can binary search for the start index once we find it using binary search. Yeah, and then once we find a valid start index for our current end index, we can store it, and then at the end we just find the minimum. Yeah, and that's how we find the minimum length of a subarray which has sum equal to target. Then we do 3 passes. First we find one subarray which has sum equal to target, and then we have essentially split the array into 3 parts. There's the first part which we just found, and then there's the array on the left and the array on the right. We can apply the function on the left and the right to find the next subarray which has sum equal to target. Once we find left and right, then we can find the minimum length of such a subarray. And then we've essentially found 2 subarrays which have sum equal to target. And we know these are the minimums because we use a greedy algorithm. We find the first minimum length, and then we find the second minimum length. And greedy algorithm works here because I don't know why it works, but there's probably just nothing better that you can do. And then at the end we just return, and if we can't find the first one or we can't find the second or third one, then we can return -1. Yeah, that was a bit of a convoluted explanation, but basically the idea is to use prefix sums and the idea of the classic 2-sum problem. Problem 4, allocate mailboxes. Given the array houses and an integer k where house I is the location of the ith house along a street, your task is to allocate k mailboxes in the street. Return the minimum total distance between each house and its nearest mailbox. Okay, so there's 2 parts to this problem. First part is determining the minimum total distance between each house and a mailbox placed in the center of that group of houses. So if we have 5 houses, this function will return the minimum total distance to a mailbox placed in the very center. And the very center doesn't have to be the very center. It just has to be a house that is near the center, or a house that is on the left or right of the center. And this works because, when you're summing intervals, it doesn't matter where you're summing from. For example, if we have these houses at 1 and 4, placing this mailbox anywhere in the center of these 2 houses will yield a sum of 3. What this means is we can just create a function that takes a start house and an end house and returns the total distance from a mailbox placed in the center to every house in that range. We can do this using some n-squared algorithm. It's not very complicated. Basically, every time we add a new house to the range, we just have to add the distance from that new house to the center because that's the optimal way to do it. And the second part is dynamic programming. So the state is going to be you have a row and a column. The row describes how many mailboxes you're allowed to place, and the column describes how many houses you have to have mailbox access to. So the first row is pretty simple. Basically, we only have 1 mailbox. So we just use our previously created function to say, okay, we're going to place a mailbox in the center of the first house to the nth house, and then we're going to find the total sum from the mailbox to all houses. That's the first row. The second row and all following rows are a bit more complicated. Essentially what we do here, so let's look at this example. Okay, we have 5 houses here. Okay, so if we're allowed to place 2 mailboxes, we can consider how many houses the first mailbox is going to cover. So if the first mailbox is going to cover 1 house, that's going to be a distance of 0, and the second mailbox has to cover these 3 houses. Or the first mailbox can cover 2 houses, and the second mailbox covers 2 houses. or the first mailbox covers 3 houses and the second mailbox covers 1 house. We can compute this by using the DP table. The first mailbox can be computed using the DP table, and the second mailbox can be computed using our function. What this means is we can compute the next row of the DP table. And for 3 mailboxes, we can say, okay, we're just going to ignore each of the individual first two mailboxes. We're going to just say how many houses they're going to have to cover. And then if the first 2 mailboxes cover 3 houses, the third mailbox is going to have to cover 2 houses. So that's how we do the DP table and the transition. Yeah, so the DP transition is right here. And at the end, we can just consider if we have k mailboxes and we have to cover all of the houses. And that is the last value in the DP table. And that's it. Like, explaining dynamic programming problems is always a bit difficult, but hopefully I'm getting better at it. Maybe I'm not, but I'm trying to get better. So yeah, so this was a good contest for me. I got top 200 and no bugs, which is pretty surprising considering that I almost always get a few bugs on some of these problems. So yeah. Also, school is basically over for me, which means I'm going to be able to do the LeetCode video finally and write up solutions and make a solution video. So LeetCode Biweekly Contest 28, good contest. Hope you enjoyed the solutions, and feedback is always appreciated. You can put them in the comments. So thanks for watching. Bye.